Yes, I'm very happy and glad to welcome so many participants to our today's session. And before we actually start to dive into our today's topic, I would like to make sure that everybody can hear me, that your audio is working well. Guys, you have a button in your webinar software which is looking like a hand. This is the raise your hand button. And I would ask you please to click this button in the case you can hear me loud and clear. Yes, I see first hands. Great. Okay, and in the case the audio connection should refuse or not work very good, please try to rejoin the session. Or in the case you have problems with your sound card or sound device, you can also use one of our toll-free audio service numbers to dial into the sessions. You can see the numbers here in the table, and here's the access code you have to enter. Well, okay, then let's start. First of all, I would like to introduce myself. My name is Milad. I'm working at SimScale for more than 2 years now as a marketing project manager, and therefore one part of my responsibilities is to make sure that new users get used to SimScale as fast as possible. I have, by the way, a mechanical engineering background myself. I've studied mechanical engineering, and I am, yes, involved in the simulation business for more than 10 years. So I have more than 10 years engineering simulation experience, which I would like to share today with you. Yes, and first of all, what is the idea of this workshop? Well, with SimScale, we have a first open web-based CAE platform, which you can use without installation. But one thing is to have access to tools, the other is to know how to use them. And that's exactly why we've created this webinar. The idea is, guys, to show you, first of all, how simulation can help you in general to improve your products. Then show you how SimScale is working, so to make you able to set up your own simulation, and for sure to answer all your questions. And when this, or with participating this webinar, the idea is that you will from then on be able to teach yourself and to become a simulation expert in a short time. On the other hand, since this is a very hands-on webinar, very hands-on session, this cannot be a detailed training about simulation theory in general, for example. So if you're interested more on the, let's say, academic part of simulation, like what are the fundamental and the governing equation behind it, which schemes and algorithms are used, you should maybe try to go to university class. There are a lot of classes about numerics and simulation theory, and there are also some good books. But in the case you're very hands-on and you want to start with simulation, then this is absolutely the right webinar for you. And also, if you really need a very wide practical training about how to use SimScale in your for your commercial product development, for this we are offering our professional training. By the way, you can win such a professional training for free by taking part at one of our workshop series, like our current workshop series about 3D printing. And taking part and doing homework for this workshop series will qualify you for free training, by the way. Yes, and a lot of people also ask, why are we scheduling such webinars? Yes, first of all, we really believe in the idea of engineering simulation, and we hope that with this, we can help a lot of people to get started very, very quickly with simulation. And on the other hand, we are a young company, we have a very innovative new product, and we would love to get your feedback and your ideas about engineering simulation and SimScale. So if you have some product feedback for us, please let me know. You can send an email to me or contact one of my colleagues. Okay, yes, and before we start with the live demonstration, because today I will do a live demonstration with you and we will together optimize the product using SimScale, let's maybe first just together explore SimScale or the SimScale website, because SimScale, as you know, is not a software you can download and install. SimScale is software as a service, and therefore our website is the main page. Yes, you should access if you want to work with online simulation. And first of all, yes, this is our website. And this video, by the way, is showing very nicely, underlining what is our idea. We want to help you guys to make better products in a shorter time. And this is independent from the application or the industry you're working on. We think we're supporting a lot of different analysis types, And yes, but first of all, we have our so-called community, and there we have one thing I think is very special about SimScale. As you guys know, SimScale is completely web browsed, and it's not only that we're providing a web-based CAE tool, but we are also providing the world's largest web-based library for CFD and FEA simulation. So this is our public project library. You can access them at www.simscale.com/project, and here you can see all public projects. Whenever you guys create a project and make it public, it will be here. And it can help other people to set up their simulation. And here, for example, we have, so if you really want to get started with a concrete application, let's say you're interested in let's say aerodynamics, for example, then you can just open this project here. You get all information about the project, and you can copy the whole project to your own workspace and, for example, use it as a template for your simulation. And in this case, for example, you could just replace this geometry by your own car design, run the operations again, and you would get a CFD aerodynamic simulation of your car design. And beside this community, we also have a forum, which you can find here. And this forum is the place where you can find instant help in the case you have problems with a project. We have different categories, like a collaboration community category, where you can look for others to collaborate on a bigger project. For every project that is public, we're automatically creating also a forum entry. And then, for example, you can discuss with other people about your projects, which is really, really nice. Yes, and I mentioned before that we have a workshop series where you can win a free professional training, and we're offering on a regular basis workshops to different, very different topics. For example, right now we have a workshop about 3D printer design, and during this workshop participants will learn how to develop and optimize different parts of 3D printer with using SimScale. It's not too late to register and attend. We already had the first 2 sessions, but you have still time. We have a recording of the sessions, and as I mentioned, you can win a free professional training. Yes, besides this, if you want to learn simulation, we also have a lot of nice learning resources. First of all, on the website, we have this whole section learning, and there we have for every kind of flavor resources to learn simulation and getting started with SimScale. For example, we have on the tutorials, we have our video tutorials, where we have a kind of course for CFD and a course for FEA. We also have a documentation where you can, if you have a question, for example, about, let's say, you don't know what turbulence model is, then you can just research it on our documentation. And we for sure, beside documentation, video tutorials, we have also these workshops and webinars where you can also access all the workshops. We have a blog, FAQs, and our professional training. Yes. Okay. Then let's now, maybe before we go to our demonstration, talk about simulation in general. A lot of people ask, why do we need simulation at all? I mean, a lot of nice products like spaceships, rockets, and airplanes were developed without any kind of simulation. And that's first of all basically not true, because simulation is used for more than 40 years in specific industries. And on the other hand, that's not the reason. In general, why simulation can really help you to improve your product design process. Just imagine you're a company working in a company which is designing and manufacturing and shipping valves. And yes, your boss just asks you and your team to create a new valve. You get a specific loads, for example, a specific use case where this valve should be used in. And the standard process would be to design, first of all, a first prototype. And design a first prototype means really to design it. So in the end, what is from the physical principle working as a valve is this outer valve body and the inner valve body. but the valve is made from more than 3 parts. For example, this assembly has like 40 different parts. And all these other parts, like the small seals, springs, etc., they have to be designed also if you want to design a full physical prototype model. And so you spend a lot of time designing one version, then you have to physically prototype it, to test it, and then you can do a design change. And this is a very, very long, time-consuming and expensive design cycles. And when you have engineering-based product development or simulation-based product development, you have a completely different process. Instead of designing the whole prototype at the beginning, you can just design a rough, let's say, a rough initial state. You don't need to design the seals and the springs because the fluid flow simulation don't care about this. And then you can just do simulations, redesign in very fast, cheap, and short cycles. And that will allow you to develop a product faster and better. To give you an example, for example, in Formula One, which is also called the pinnacle of racing and engineering, CFD, so fluid flow simulation, plays a very important role. And if they, for example, want to design a new front wing, right now they're doing first of all 100 CFD simulations of just of the section of the cross section of the wing. Then they're doing based on the best 30 cross section. They're simulating 30 3D simulations, and then the best 10 out of them are physically tested. And so that can save time, money, and create better results. Just in general, if you have any questions, just let me know. Write them, please, in this question window. And then I will, whenever I have time later at the end of the session, talk with you about your question. Okay, and last thing before we start with the actual demonstration. And what is SimScale right now? As I mentioned, SimScale is more than just an end-to-end CAE platform in your web browser. It's a simulation ecosystem. What does I mean with that? Yes, with SimScale, what I already showed you, you have access to a full 3D CAE simulation environment through your web browser without installation, software update, license cost. But on the other hand, it's more than that. We are also bringing content together. We have hundreds of ready-to-use high-quality simulation projects, reusable simulation setups, and we bring also people together because simulation experts, enthusiasts, students, and researchers from all over the world are part of the SimScale platform. And therefore, the idea of SimScale is really not only to provide you with the tools, but provide you with everything you need to use simulation successfully in your company, and which will help you to save money and design better products. Last but not least, let's take a look at our pricing model, because as I mentioned, basically to use SimScale is absolutely free. Everybody can get a free community account, and community account means you have access to all features. You have 3,000 core hours computing time, because at SimScale we are not talking about licenses, we are just in the end paying what you're using. In this case, you're paying nothing for 3,000 hours of using our machines. And you have 5 GB storage for free. The only difference is that you can only create public projects with a community plan. And if you want to create professional secret project, private projects, then you have to choose one of our professional subscriptions. And now let's dive into a live demonstration. You can imagine how it was to be a valve designer 5 minutes ago. And let's just continue this role game. Just imagine you get, in the end, 2 design ideas from your designer. The first design idea is this one, design 1 on the left side, which is more sharp. And then we have this more smooth one with smooth edges on the right side, design number 2. And if we now take a look at this, or compare this to geometries, it's obvious what the differences. Design number 2 is like more material or more fluid of domain, a domain of fluid. Just to make you should keep in mind that in the end what we're showing here is a cross section of the valve, and this is also the inner volume. And so this yellow area is where we have the difference. And now when it comes about designing a valve, I mean, what is the aim? And the aim of a valve in the end is, also the function is to control a volume flow rate or mass flow rate. But that's another very important name, that this control of this flow rate should not have a big pressure drop. What does it mean? If you would just take let's take a pipe and put inside the pipe a valve and make this valve completely open, you will have a change in pressure and therefore a change of loss of energy. And this loss of energy has to be, or this energy has to be added externally from the pump to the system, so it's destroying efficiency. And therefore, our design goal is to minimize the pressure drop on the first hand, so that we have the best efficiency possible, and also secondly, to homogenize the outflow, because nobody wants unhomogenized flow coming out of a pipe. Then the operation conditions are, we have a mass flow of 8 kilogram per second, and we are using water with a standard density of 1000 kilogram per and we will, yes, perform a fluid flow simulation of this valve. And for this, we have this original CAD model of the valve, and we only need this red volume inside the flow volume, since we're doing a simulation of the fluid cell flow inside the valve and not outside. I hope that's clear why. And yes, now let's switch to the platform. So just to describe what we will do now, we will now open a project with already uploaded a CAD model. We will, once this is done, we will create a so-called mesh. And now this is for some people confusing who are never in touch with simulation. Basically, this is all simulation tools. What they're doing is they're taking governing equations about flow or about solid mechanics and apply them on a concrete design. But these equations, you cannot solve them analytically. They are quite complex. You have to solve them numerically on a computer for discrete points. And this is also very important. If we get, for example, the pressure distribution out of a simulation, it's only discrete. We have not the pressure for every point. And therefore, you have to tell this code where it should locally calculate pressure, velocity, and all the other physical quantities. And that is done with so-called meshing. And this only means that you're dividing your geometry into smaller parts, as you can see here. And as smaller this mesh is, as more precise will the simulation result be. And at the end, then we do it. After we have mesh, we can do the simulation setup, so decide how the model is interacting with it in the environment and take a design decision. Okay, so let's switch to the platform. I have prepared a project here already containing the two geometries of the valve. And just to show you how it will basically work, you can also upload your own geometry, but just clicking on Upload Geometry, give a name to it, select the file format, and then you can just choose it and which file, and you can even upload zipped files. By the way, our simulation library is also a kind of CAD library with hundreds of different CAD models, just for you to know. Okay, now we will create a mesh. I will just demonstrate all the steps for one design, but do it for the other design will be exactly the same. And first thing I have to do is, as I mentioned, to create this mesh. So I create a new mesh project. Then I will select the geometry, which I will use as a base for my mesh. And then I just have to add a mesh operation. In our case, we would use this so-called automatic snappy hex mesh for internal flow, which is this dedicated meshing algorithm who is for fluid flow simulation, which is working nearly completely automatic. But for sure, we also have a lot of other meshing options, like you can do the snappy hex meshing manually. We have assistant for external flow, and we have also TED measures and the different versions like full automatic, half automatic, which you can also use for FEA simulations and so on. And what's good thing is with automatic automatic snappy hex mesh for internal flows, we just have to choose a fineness for the mesh. So let's say moderate 3, the number of cores, so how many processors we will use to accelerate the computation, and then we can decide if we want to have layers on surface. And layers just means that your mesh is finer in the near of the wall, and it's a special kind of one-directional refinement. That sounds abstract, but you will right now see what it means, which helps to have the perfect balance of accuracy and simulation speed. And we will just put it everywhere except on in and outlet. That's the only reason for this. So keep this in mind. Never put on non-physical walls like inlets and outlets or layers. And instead of selecting now all other cells, we'll just select the only two faces we don't want to have layers and invert our selection. Then we can add selection from viewer, save it, and that's it. And now we have set it up everything for the mesh. We can just start the mesh operation. And I've already for sure prepared such a mesh for you guys. So this is the same project. And this is how the mesh will look. And here you can also see what I mean when I was talking about this layer elements. These are these layers. And this is one directional, only normal to the surface growth of the cell size. Okay, yes, and this is our mesh. And when the mesh is done, you will get notified. And then you can also, for example, here check if everything is fine with your mesh. Okay, then let's do a quick wrap up. What I showed you how to import CAD geometries. We talked about the Automatic Snappy Hex Mesh, which is a meshing tool dedicated for fluid flow simulations. And we use the internal version for internal flow. And we talked about layer refinement, this special kind of one-dimensional refinement you need in the layer of walls. There are some topics we did not talk about today, or cannot because the time is too short, which are important but not fundamental necessary. First of all, CAD cleaning and preparation. For example, in this case, I extracted the inner volume of the valve before from the CAD model. And this CAD cleaning can be very time consuming because just imagine you want to do a fluid flow simulation of an airplane and you would not relieve all the screws at the outer surface of the plane. This 1,000 or maybe million of screws will not have a big effect in the flow simulation result, but to consider them in simulation is a lot of work. And so simplifying, cleaning up your CAD model is essential and can take time. And for sure, we could also talk theoretically about manual mesh setup and mesh quality assessment, which is also a little bit more advanced. Well, okay. Now we can start to set up the actual simulation. So let's create a new simulation. And here now we are asked which simulation type we want to do. And in our case, the fluid flow simulation. We could also do solid mechanics simulation, thermostructural simulation, acoustic simulation, or particle simulation. And for example, in our case, now we have a lot of different opportunities. And we have an incompressible flow since we're doing water. We have a turbulent flow. Turbulent, I think you all can imagine what turbulence is. When you look, for example, behind the airplane, you can sometimes see these eddies. And this is that means that the flow is due to the high so-called Reynolds number. It's a turbulent flow. And this has to be handled another way by the solver. But we want to have a steady state simulation. Steady state means that we want to have a snapshot of the results, average result, and not for every time step because the flow can change with time. And now automatically our simulation tree is built, and now we have just to follow this path to get our simulation done. So first of all, we'll now have to choose the mesh. We will choose this mesh here of our design number 2. Then we have to assign a material. We can access our material library and add it to the mesh. And now we've automatically applied the material properties of water to this mesh. And here you can, for example, check all the other properties like density, etc. Okay. Then we have initial conditions, boundary conditions. Initial conditions and boundary conditions, to understand them, you have to know that our simulation tools are solving iteratively the simulation. That means that they're calculating it again and again. With every calculation step, the results become better and finer. But therefore, you need an initial state, and these are your initial conditions. You can leave them blank for pressure and velocity, because, to be honest, 0, 0, 0 then is the best value, because you're applying then these values to the whole flow domain. Only exception is K and omega. K and omega are these so-called turbulence parameters, and they are used to describe turbulence. You can calculate them for your application using some Excel forms or online tools. It's very easy, and we will just have to add them here because they are used later on, and with 0, 0, 0 it will not work. So just enter them here. And the only thing we have to do right now is just to describe now with the boundary condition how it is interacting with the environment. Okay, so let's start. First of all, let's start with what is obvious, the inlet. So this is the inlet, the kind type, it's a velocity inlet, and it's the inlet flow rate. These are just different ways to describe the same things, but it's for us easier just to calculate with the flow rate than with velocity. Okay, density is automatically updated from the material model, so we just have to add 8 kilo per second. And done. Then we have an outlet here. And this is a so-called pressure outlet. Since the pressure is constant and it's an outlet, because the back pressure has to be constant, the reference pressure, just choose the phase, save. And finally, we have the remaining walls. We will do the same. Select inlet and outlet, invert the selection, call it walls, type wall, and it's a very important, a non-slip wall. And now we select all the other walls, and done. Wait, finally we can tune a little bit the numerics. This is not very important. This is just make simulation faster. Yes. Okay. And now we can do simulation control. So we want to do 1000 iteration steps, 1000 steps to make simulation result finer. We only want to save the final result using 8 cores and a maximum runtime of 2 hours. And now the last thing is a so-called result control item. That means that I just want to be something to be calculated out of the results during the calculation. In this case, I want the area average of the pressure drop. And now this is a little bit tricky, but if you think about it, it makes sense. The pressure drop is in the end the change of average pressure between inlet and outlet. The outlet pressure is fixed. Therefore, we can just take, and it's 0 because if you take a look back, let me save this first. If you take a look back, we have a reference pressure of 0, and therefore the pressure here, since this is 0, the pressure here is the pressure drop directly, which is, and so the average pressure of this phase is our pressure drop. Okay, now we're done. We can check the simulation, create a new run, and then we can start it. And yes, just to wrap it up again, which step we showed you, we together assigned the mesh and defined the material of the fluid. We defined the boundary conditions, there only turbulence parameters K and omega, and the boundary conditions, inlet, outlet, and walls, and a result control item. And there are also some stuff we did not talk about, but which we could theoretically would be turbulence modeling, to go more into details for this. And we could also, some other advanced topic would be numerical solver setting and advanced solver settings. Well, now I've for sure prepared again a simulation including the results, since this can take up to half an hour. And then you will get notification that your simulation is finished. And then you get, yes, this plot here. This is a convergent plot. And in the end, what it's showing, it's for every iteration, for every step, how the average error changed. And the average error became smaller and smaller and converged here. So this is looking good. For example, the average pressure of error of pressure is smaller than 0.01. And the average error of velocity in y direction is like 1e minus 3. Okay, I saw we have 2 questions. Guys, can you please wait 5 minutes and we will have only time for your questions. Okay, and then we can switch to the post-processor. This is a beta version, so I would suggest to do all your post-processing locally right now since we are still developing it. And you can download this tool for free here, clicking on this button. And once the simulation is done, you can also take a look at your convergence plot again here. And you can also take a look, for example, on pressure, on this average pressure we calculated, and also on K and the velocities. And this is very important because that becomes constant, and that really is a good sign that our simulation is stable and the results are good. And now let's take a look inside the simulation. Therefore, we click on the solution fields, and that will open a menu or window where we can interact in 3D with our simulation result. Okay, that takes some seconds because the data have to be added to the viewer. And now we have here the mesh. Then we can first of all, we'll jump to the latest simulation time step. So let's example here, visualize, let's say pressure here. And this, guys, makes absolutely sense since we initialized pressure with 0. Therefore, it's everywhere 0. But if we jump now to the last simulation step, where we have, then we will get a different result. So this is the pressure distribution in this valve. And now we can use different filters to take a look inside. For example, we can do a slice filter, which is creating a slice now. And now we have a slice. And then we can, for example, here represent pressure if we want to, velocity, we can also generate screenshots automatically, and we can even, for example, create other nice things like streamlines. And then we even have streamlines inside. And if we now take a look at the pressure here, then we can have the pressure drop here. And this was around 12, this is around 10, so with a difference of over 10%. Well, okay. That was for post-processing. I showed you the convergence plot, how to check the result control data, the pressure, and how to create slices and streamlines. And every advanced topic would be here to derivate additional physical quantities out of the existing ones and do local post-processing. Great. Then I would suggest let's take a look at the results because I prepared a kind of result analysis, and then we have time for your question, guys. First of all, again, you can see we have left our design 1, this is design 2. And here you can see this is the velocity distribution, and blue is low and green is, or red is high velocity. And what you can see first of all, let's get back, the streamlines, is that the flow is looking much more chaotic here than there. If you take a look at the flow velocity profile, it becomes obvious that here we have high inhomogeneous part of the flow at the outflow, and that we have more, let's say, dead area. For example, here, here, and here. There's a dead zone because flow is separating. If you take a look at the pressure, you can see just optically, because that's exactly the same color range, that the pressure in average is higher in this inner valve body for design 2 than for design 1. And if you now take a look exactly at the pressure drop, we have 17% less pressure drop. And why, you may be asked, why 12 became to 12,000? The reason is that pressure in SimScale is divided by density automatically. So it's a relative pressure. And yes, For the absolute value, you have to multiply it with 909 with the density. If we would, for example, now go through the valve, so start at the beginning here and go like this through the valve, and this is design 1, this is design 2, and then you can really see how designs change. For example, here you have this smooth part, which is creating a kind of extra space, and then you can really see here why you have this higher pressure loss. Because if you look here, you have here this low pressure area, which is completely missing here. And this is creating this additional pressure loss. And here you can also see how much more homogeneous the upper version is than the lower version. Great, guys. Thank you very much for your time. And now we have, yes, I have time now to answer all your questions. And I will start with Adam. Adam asked if this webinar will be recorded and distributed afterwards. Yes, we will record this webinar and send it to you maybe beginning of next week. So you can also watch it again. Kiel wants to know if he can create a surface to use for result monitoring before simulating. Dear Kiel, is it right now not possible at SimScale, but you can do it in post-processing and pair review locally afterwards and create zero surface and, for example, measure flow through the surface. Is that what you mean? Okay, Kiel, great, thank you. Okay, are there any other questions? This is your chance, guys. For sure, you can reach out to me or my colleague whenever you want, but if you have any question, just ask it now and I will try my best to answer it. Okay, seems not to be the case. Then thank you very much for